Section: Introduction. In this section, we discuss the significant advancements made in generating photorealistic humans in both 2D and 3D. We attribute much of this success to the effective estimation of various elements like 2D keypoints, detailed body part segmentation, depth, and surface normals. However, accurately estimating these elements remains a challenging area of research, and complex systems designed to enhance performance for specific tasks can limit broader use. Additionally, gathering precise ground truth annotations in real-world settings is notoriously hard to scale. Our aim is to create a unified framework and models that can infer these elements in real-world scenarios, enabling a variety of human-centric applications for everyone. We believe that effective human-centric models should meet three key criteria: generalization, broad applicability, and high fidelity. Generalization allows the model to perform reliably in new conditions, while broad applicability ensures it can handle various tasks with minimal changes. High fidelity means the model can produce accurate, high-resolution outputs, which is crucial for realistic human generation tasks. We present our models, collectively named Sapiens, which embody these qualities. We emphasize that leveraging large datasets and scalable model architectures is essential for achieving generalization. For broader applicability, we adopt a pre-train then fine-tune strategy, which allows us to adapt the model to specific tasks after initial training with minimal adjustments. This raises an important question: what type of data is best for pre-training? Given our computational limits, should we focus on gathering as many human images as possible, or is it better to pre-train on a less curated dataset that reflects real-world variability? To explore the impact of pre-training data distribution on human-specific tasks, we have compiled the Humans-300M dataset, which includes 300 million diverse human images. We use these unlabeled images to pre-train a series of vision transformers from scratch, with model sizes ranging from 300 million to 2 billion parameters. Among various self-supervised learning methods, we select the masked autoencoder (MAE) approach for its simplicity and efficiency, allowing us to process a larger number of images with the same computational resources. For higher fidelity, we increase the input resolution during pre-training to 1024 pixels, which significantly boosts computational demands compared to existing models. Each model is pre-trained on 1.2 trillion tokens. We also utilize a consistent encoder-decoder architecture for fine-tuning on human-centric tasks, initializing the encoder with pre-trained weights and the decoder randomly. We focus on four main tasks: 2D pose estimation, body part segmentation, depth, and normal estimation. We confirm the importance of label quality for the model's performance in real-world scenarios. Public benchmarks often contain noisy labels, which can lead to inconsistent training signals. Therefore, we emphasize the need for precise annotations to align with our goal of 3D human digitization. We introduce a denser set of 2D keypoints for pose estimation and a more detailed class vocabulary for body part segmentation, exceeding previous datasets. Specifically, we present a comprehensive set of 308 keypoints covering various body parts and expand our segmentation vocabulary to 28 classes. To ensure high-quality annotations, we use a multi-view capture setup for pose and segmentation data. We also incorporate human-centric synthetic data for depth and normal estimation, utilizing detailed scans to create high-resolution depth maps and surface normals. Our findings show that combining large-scale pre-training with high-quality annotations leads to strong generalization in real-world applications. In summary, we introduce Sapiens, a family of vision transformers pre-trained on a large dataset of human images. Our study demonstrates that effective data curation and large-scale pre-training can significantly enhance model performance within the same computational budget. Our models, fine-tuned with high-quality or synthetic labels, exhibit strong generalization in real-world scenarios, achieving state-of-the-art results in 2D pose estimation, body part segmentation, depth, and normal estimation. Section Summary. In this section, we discuss our development of Sapiens, a unified framework of vision transformers designed for robust human asset estimation in real-world scenarios. We emphasize the importance of large-scale pretraining on diverse datasets and high-quality annotations to achieve generalization, broad applicability, and high fidelity in tasks such as 2D pose estimation and body part segmentation. Section: Related work. In this section, we explore the boundaries of training large models using a vast number of real-world human images. Our work builds on previous research in several areas: large-scale pretraining, human vision tasks, and large vision transformers. For large-scale pretraining, we note that the success of training models on extensive datasets for language tasks has become a standard approach. Similarly, computer vision is increasingly adopting large datasets for pretraining. Datasets like LAION5B, Instagram 3.5B, and others allow us to work with data far beyond traditional benchmarks. Key contributions in this area include DINOV2, which excels in creating self-supervised features, MOZ, which examines the scaling of masked autoencoders on billions of images, and AIM, which looks at autoregressive visual pretraining akin to BERT for vision transformers. Unlike these methods that focus on general image pretraining or zero-shot classification, we take a human-centric approach by using a large collection of human images for pretraining and then fine-tuning for various human-related tasks. In terms of human vision tasks, we recognize that achieving large-scale 3D human digitization is a significant goal in computer vision. While we have made strides in controlled environments, challenges remain in applying these methods to real-world settings. Therefore, we aim to create versatile models that can perform essential tasks like keypoint estimation and depth estimation in natural environments. Regarding scaling architectures, we observe that the largest publicly available language models have over 100 billion parameters, while typical models have around 7 billion. In contrast, vision transformers have not been scaled similarly, with most existing models ranging from 300 million to 600 million parameters and pre-trained at a resolution of about 224 pixels. To fill this gap, we introduce Sapiens, a set of large, high-resolution vision transformer models that are pre-trained at a resolution of 1024 pixels using millions of human images. For our method, we utilize a proprietary dataset of approximately 1 billion in the wild human images for pre-training. We pre-process this dataset by removing images with watermarks, text, or unnatural elements and filter it using a bounding box detector to keep only high-quality images. Our dataset includes over 248 million images with multiple subjects. In our pre-training process, we adopt the masked autoencoder approach. Our model learns to reconstruct original human images from partial observations. It consists of an encoder that creates a latent representation and a decoder that reconstructs the image. We resize all images to a fixed square size and divide them into non-overlapping patches. A portion of these patches is randomly masked, and we maintain a consistent masking ratio throughout training. Our model demonstrates strong generalization across various image characteristics, and even with a high masking ratio, it can effectively reconstruct human anatomy in unseen samples. Section Summary. In this section, we explore the advancements in training large architectures using extensive human image datasets, highlighting our human-centric approach that focuses on pre-training with nearly 1 billion in the wild images for various human vision tasks. We also introduce our Sapiens models, which utilize a masked autoencoder technique to achieve effective image reconstruction and generalization across diverse human characteristics. Section: 2D pose estimation. In this section, we focus on 2D pose estimation, following a top-down approach to identify the locations of key points from an input image. We treat this task as predicting heat maps, where each heat map indicates the likelihood of a key point being at a specific location. We introduce a pose estimation transformer, which we denote as P, for detecting these key points. During both training and inference, we scale the bounding box to match the image dimensions and input it into P. We represent the ground truth key points as K heat maps, denoted as Y, corresponding to the input image I. The pose estimator transforms I into predicted heat maps, represented as hat Y, where hat Y equals P of I. We train P to minimize the mean squared error between Y and hat Y. For fine-tuning, we initialize the encoder of P with pre-trained weights and randomly initialize the decoder. We set the aspect ratio to 4:3 and adjust the positional embedding accordingly. Our lightweight decoders utilize deconvolution and convolution operations. We fine-tune P across various skeletons, including those with 17, 133, and a new detailed skeleton with 308 keypoints. Our annotations include 243 facial keypoints, surpassing existing datasets that typically have up to 68, allowing us to capture intricate facial expressions. We manually annotated 1 million images at 4K resolution from an indoor setup. Next, we discuss body part segmentation, also known as human parsing, which classifies pixels in the input image into C classes. We convert this task into estimating per pixel class probabilities to create a probability map, hat P, where hat P equals S of I, with S being our segmentation model. We use the same encoder-decoder architecture and initialization for S. We fine-tune S to minimize the weighted cross-entropy loss between the actual and predicted probability maps. We fine-tune S using two vocabularies, a standard set with 20 classes and a larger set with 28 classes. Our new vocabulary improves upon previous datasets by distinguishing between upper and lower limbs and including detailed classifications like upper, lower lips, teeth, and tongue. We manually annotated 100,000 images at 4K resolution with this vocabulary. For depth estimation, we adopt the segmentation architecture but modify the decoder to output a single channel for regression. We denote the ground truth depth map of image I as D, and the depth estimator as D, where hat D equals D of I. We normalize D to a range between 0 and 1 for relative depth estimation. The depth loss, L_depth, is defined based on the logarithmic difference between D and hat D. To develop a robust monocular depth estimation model, we render 500,000 synthetic images using 600 high-resolution human scans. We select random backgrounds from a collection of 100 HDRI environment maps and position a virtual camera in the scene, adjusting its focal length, rotation, and translation to capture images and their corresponding ground truth depth maps at 4K resolution. Section Summary. In this section, we describe our approach to 2D pose estimation, body part segmentation, and depth estimation using a top-down paradigm and encoder-decoder architectures. We utilize heat map predictions for keypoint detection, classify pixels into detailed body part categories, and implement a depth estimator, all while leveraging extensive manual annotations and synthetic data to enhance model performance. Section: Surface Normal Estimation. In this section, we focus on surface normal estimation. Similar to our previous tasks, we set the output channels of the normal estimator to 3, which represent the x, y, and z components of the normal vector for each pixel. We also use the generated synthetic data to guide our surface normal estimation. We define the ground truth normal map for an image as n, and the estimated normal map as hat n, which we obtain from our normal estimator. Next, we provide an overview of our implementation details. We conduct extensive benchmarking across 4 tasks: pose estimation, part segmentation, depth estimation, and normal estimation. Our largest model, Sapiens 2B, is pre-trained on 1024A100 GPS for 18 days using PyTorch. We utilize the Atom W optimizer for all experiments, with a learning schedule that includes a short linear warm-up, followed by cosine annealing during pre-training and linear decay during fine-tuning. All models are pre-trained from scratch at a resolution of 1024 by 1024 pixels with a patch size of 16. For fine-tuning, we resize the input image to a 4:3 ratio of 1024 by 768 pixels. We apply standard augmentations such as cropping, scaling, flipping, and photometric distortions. Additionally, we incorporate random backgrounds from non-human COCO images for segmentation, depth, and normal prediction tasks. We also implement differential learning rates, using lower rates for the initial layers and progressively higher rates for the later layers. The layer-wise learning rate decay is set to 0.85, with a weight decay of 0.1 for the encoder. We summarize the design specifications of Sapiens in a table. We prioritize scaling our models by width rather than depth. Notably, the Sapiens 0.3b model, while similar in architecture to the traditional VIT large, has 20 times more floating point operations due to its higher resolution. For 2D pose estimation, we fine-tune Sapiens for face, body, feet, and hand pose estimation using our high-fidelity annotations. We train on a dataset of 1 million images and evaluate on the human's 5K test set, which contains 5,000 images. Our evaluation is top-down, using an off-the-shelf detector for bounding boxes and performing single human pose inference. We compare our models with existing methods for whole body pose estimation, focusing on 114 common keypoints between our 308 keypoint vocabulary and the 133 keypoints from COCO whole body. Sapiens 0.6b outperforms the current state-of-the-art DW pose L by 2.8 average precision, AP. Unlike DW pose, which employs a complex student-teacher framework, Sapiens uses a general encoder-decoder architecture with extensive human-centric pretraining. Interestingly, even with the same number of parameters, our models show better performance than their counterparts. For example, Sapiens 0.3b exceeds VIT pose plus L by 5.6 AP, and Sapiens 0.6b outperforms VIT pose plus H by 7.9 AP. Our results indicate a direct relationship between model size and performance within the Sapiens family, with Sapiens 2b achieving a state-of-the-art score of 61.1 AP, a notable improvement of 7.6 AP over previous work. Despite fine-tuning with indoor capture studio annotations, Sapiens demonstrates strong generalization to real-world scenarios. For body part segmentation, we fine-tune and evaluate our annotations using a segmentation vocabulary of 28 classes. Our training set consists of 100,000 images, while the human's 2K test set contains 2,000 images. We compare Sapiens with existing body part segmentation methods that have been fine-tuned on our training set, using the recommended pre-trained checkpoints for initialization. Similar to pose estimation, we observe good generalization in segmentation results. Notably, our smallest model, Sapiens 0.3b, outperforms leading segmentation methods like Mask2 Former and DeepLab v3+ by 12.6 mean intersection over union, MIOU, due to its higher resolution and extensive human-centric pre-training. Additionally, increasing the model size enhances segmentation performance, with Sapiens 2b achieving the best results of 81.2 MIOU and 89.4 mean accuracy on the test set. We also present qualitative results of our models. Section Summary. In this section, we describe our approach to surface normal estimation using a decoder that outputs the normal vector components for each pixel, and we detail our implementation of the Sapiens model, which is pre-trained on a large dataset and fine-tuned for various tasks, achieving state-of-the-art results in pose and body part segmentation. Our experiments demonstrate that larger model sizes correlate with improved performance across all evaluated tasks, with Sapiens 2b setting new benchmarks in accuracy. Section: Depth Estimation. In this section, we evaluate our models for depth estimation using the Thuman 2.0 and High 4D datasets. Thuman 2.0 includes 526 high-quality human scans, from which we create 3 image sets for testing: face, upper body, and full body, resulting in 1,578 images. This allows us to assess our model's performance on single human images at different scales. In contrast, the High 4D dataset focuses on scenarios with multiple humans, featuring sequences of 2 subjects interacting. We select sequences from pairs 28, 32, and 37, which includes 6 unique subjects from camera 4, totaling 1,195 multi-human images for testing. We adhere to the evaluation protocols set by Midas v3.1, reporting standard metrics like absolute relative error and delta 1. Additionally, we use root mean square error as our main metric since delta 1 does not adequately capture performance in scenes with subtle depth changes. Our models are compared with existing state-of-the-art monocular depth estimators, and we find that Sapiens 2B, trained only on synthetic data, significantly outperforms previous models across all scales. We observe a 20% reduction in RMSE compared to the best-performing depth anything model on high 4D images. It's noteworthy that while baseline models are trained on diverse scenes, Sapiens specializes in human-centric depth estimation. We provide a qualitative comparison of depth estimation between Sapiens 1B and depth anything L, ensuring a fair comparison by renormalizing the predicted depth using the human mask. For surface normal estimation, we use the same datasets as for depth estimation. We report the mean and median angular error, along with the percentage of pixels within specific angular errors. Our models outperform existing human-specific surface normal estimators by a significant margin, with Sapiens 2B achieving a mean error of around 12 degrees on both Thuman 2.0 and high 4D datasets. We also qualitatively compare Sapiens 1B with PIF-UHD and Econ for surface normal estimation, noting that PIF-UHD is trained on the same 3D scans as ours, while Econ uses a larger set of scans. In our discussion, we emphasize the importance of the pre-training data source. The quality of features is closely tied to the quality of pre-training data. We assess this by pre-training Sapiens 0.3b on various datasets under the same conditions and then fine-tuning for each task. We explore the effects of pre-training on general images versus exclusively human images, creating datasets with 100 million and 300 million general images from our 1 billion image corpus. Our results indicate that pre-training with a human-centric dataset leads to better performance across all metrics, confirming the advantages of focusing on human images during pre-training. We also analyze how the number of unique human images seen during pre-training affects normal estimation performance, showing consistent improvement as the pre-training data size increases. Our models demonstrate strong zero-shot generalization across various settings. For example, in segmentation, Sapiens are fine-tuned on single human images with limited diversity, yet our extensive pre-training allows for generalization across different subjects, ages, and perspectives. However, we acknowledge some limitations. Our models struggle with complex poses, crowding, and severe occlusion. While data augmentation and a detect and crop strategy may help, we view our models as tools for gathering large-scale, real-world supervision, paving the way for the next generation of human vision models.